Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 9, Section 2 notes, all over naming and writing formulas for ionic compounds. So we want to start talking about binary ionic compounds. In the 1700s, Antoine Lavoisier and other chemists developed a systematic method for naming chemical compounds, because all too often, chemicals that they were using just had common names, like baking soda, but that became difficult to just remember all of these different compound names, so they decided to come up with a naming system. So writing formulas for binary ionic compounds. A binary compound is composed of two elements. These can be ionic or molecular. Ionic compounds are a metal and a nonmetal, while a molecular compound is two nonmetals. To write the formula for a binary ionic compound, we're going to first write the symbol of the cation and then the anion. And we're going to add subscripts as needed to balance out the charges. The positive charge of the cation must balance the negative charge of the anion. The net ionic charge of the formula will be 0. So for example, we have potassium chloride, which is composed of the K plus ion and the Cl minus ion. So it is a binary compound. And we can see that since we have a plus 1 and a minus 1, that this compound is going to be in a 1-to-1 ratio. So the formula for this binary ionic compound is going to be KCl. Now there's another method that we can look at to writing formulas for these compounds, and we're going to look at that here on the next slide. So over here we have a photo that shows a step in the process of making steel. And what they're currently making in this step is hematite, which is a common ore of iron that contains iron 3 oxide. So when we talk about iron 3 oxide and writing the formula for that, we know that iron 3 tells us that we have Fe3 plus ion, and oxide is our O2 minus anion. But we can see that these are not going to add up to give us 0, right? Plus 3 and minus 2 do not combine to give us 0. So what we need to do is find the least common multiple. And the least common multiple of 2 and 3 is 6. So we need 2 Fe3 plus ions for every 3 O2 minus ions to reach an overall net charge of 0. So that will give us 2 times 3 plus 2 times, plus 3 times 2 minus will give us an overall net charge of 0. So we can write that as Fe subscript 2, telling us we have 2 iron 3 plus, and O3, telling us that we have 3 O2 minus ions. So now we're going to look at that other trick that I was talking about on the last slide, and I like to just call it the crisscross method. So, for example, we'll take the same ionic compound. We have Fe3 plus and O2 minus. So what we're going to do here is we're just going to take the charges and crisscross them to help us figure out the formula. So we take the 3 plus and we bring it down here, and we take the 2 minus and crisscross it over by the iron. So that tells us that we have Fe2O3. So notice that we dropped the positive and negative signs. And that's because now this is representing a ratio of iron 3 plus ions to O2 minus ions. And the subscripts are always going to be represented in the lowest whole number ratio. Subscripts need to be expressed in the lowest whole number ratio, right? So when we look at compounds like calcium sulfide, we know that calcium is a Ca2 plus and sulfide ion is S2 minus. So when we do our crisscross method, we should get Ca2S2, right? But since we need to express it in the lowest whole number ratio, 2 and 2 can be reduced to give us CaS. And this is going to be the correct formula for this compound. So our next one is copper 2 sulfide. So we have Cu2 plus and S2 minus. So again, we're going to crisscross our charges, and that's going to give us Ca or Cu2S2, but then remember again, we reduce those down, CuS. Now our last one, we have potassium nitride. We know that potassium is K plus, and the nitride ion is N3 minus. So when we go and crisscross our charges, we bring our plus 1 over by the N, the 3 minus over by the K, and we're going to end up with K3N. Now we're going to name binary ionic compounds. So if you know the formula for a binary ionic compound, you can write its name. First, you're going to verify that the compound is composed of a monatomic metallic cation and a monatomic nonmetallic anion. So what that just means is that we have a metal and a nonmetal present. So we're going to place the cation name first, followed by the anion name. So when we look at our first compound here, CS2O, we know that CS is cesium, which is a metal, and that is a plus 1 cation. So we write our cation first, cesium oxide, because oxide is our anion. When we name NaBr, sodium is going to be our cation because it's a plus 1 charge. So we write sodium bromide, because remember, when we're naming negative ions or anions, we're going to cut off the ending and make it IDE, so sodium bromide. And that last compound there, SrF2, strontium is going to be our cation, so we write strontium fluoride. Sorry, I'm running out of room here. But that's how we're going to name it. So we name it by writing the cation name first, followed by the anion name. So let's suppose we want to name the binary compound CuO. The name copper oxide would be incorrect, because copper commonly forms two cations, right? Cu plus and Cu2 plus. And we know this from that big chart that we had to study from. So how can we tell which of these cations forms the compound CuO? How do we know if that's Cu plus or Cu2 plus? So the formula, when we look, CuO indicates a 1-to-1 ratio between copper and oxygen. And we know that the oxide anion is always a -2 charge. So therefore, the charge of the copper cation must be a 2 plus in order to balance the 2 minus. Because we know that they're in a 1-to-1 ratio, and since oxide is 2 minus, copper must be 2 plus. So that is going to be copper 2 oxide. If the metallic element in a binary ionic compound has more than one common ionic charge, a Roman numeral must be included in the cation name, much like we just saw with copper oxide, copper 2 oxide. So when we look at our first example here, COI2, we know that CO is cobalt, and cobalt is a transition metal. And if we check our chart, it has two common charges, so it could be CO2 plus or CO3 plus. But when we look at the I minus, we know that iodide is a 1 minus charge, right? So when we look at this, we can see and we can kind of uncrisscross our charges. We can kind of bring our 2 back up by the CO and the invisible 1 that's technically next to the cobalt up above the I. So we could have cobalt 2 iodide. So when we uncrisscross, it's going to look like this. We have COI2, and we just uncrisscross like we did before. And that's going to tell us that we have cobalt 2 plus and I minus. That's how we know that it's cobalt 2 iodide. Now when we look at Li2Se, we know that lithium is a +1 charge and Se is a 2 minus because we uncrisscross. We bring the 2 back up by the Se and we bring the 1 over back by the lithium. So we can name this one cation first, lithium selenide. And if I could spell correctly, that would help us out a lot, wouldn't it? So Selenide, lithium selenide. And we don't need a Roman numeral here because lithium only exists as a +1. Seashells are made of calcium carbonate, which is CaCO3, which is not a binary ionic compound because it contains more than 2 elements. So let's remember that an ate ending or an ite ending on the name of a compound indicates that the compound contains a polyatomic ion that includes oxygen. So to write the formula for a compound with a polyatomic ion, we write the symbol for the cation followed by the symbol for the anion, and then we add our subscripts as needed to balance the charge. So if we have calcium nitrate, we know that calcium is Ca2 plus and our nitrate ion is NO3 minus. So just like we did before, we can crisscross our charges. But what we run into here is that now we have a 2 outside of our nitrate, telling us that we have 2 nitrate ions. So when we write the formula for that, we need to indicate that by parentheses. So those parentheses tell us that we have 2 nitrate ions. So now if we look at lithium carbonate, we have Li plus and CO3 2 minus. So we can crisscross those charges to give us our subscripts. And we have Li2 CO3. Now we don't need parentheses here because there is technically a subscript of 1 next to the carbonate ion. And we only need parentheses when we have 2 or more. So if we look back at calcium nitrate, we have a ratio of 1 to 2, 1 calcium for every 2 nitrate ions. And with lithium carbonate, we have a ratio of 2 to 1, 2 lithium ions for every 1 carbonate ion. To name a compound containing a polyatomic ion, we state the cation name first and then the anion name. If the cation is a metallic element that has more than 1 common ionic charge, we include a Roman numeral in the cation name. Like, for example, we have NaClO. So we know that these 2 ions are Na plus and ClO minus. Hopefully you guys know by now is ClO minus as hypochlorite. So when we write the name of this, we say sodium hypochlorite. And we don't need a Roman numeral here because sodium is not a transition metal and it only exists as Na plus 1. So here we have Fe parentheses ClO3 parentheses 3. So if we uncrisscross, we can tell that we have Fe3 plus and ClO3 minus, which is our chlorate ion. So when we write this, and since iron can exist as Fe2 plus or Fe3 plus, we need to indicate that. So we write this as iron 3 chlorate. In good news, again, we are at the end of your Chapter 9, Section 2 notes, and as always, the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, Resources CD, and at pearsonchem.com. Thanks so much. Have a good night.